And he's saying one way of preparing chloroethane is to react chlorine with ethane. So you have a reaction of chlorine with ethane in ultraviolet light. So that is that one. We've done that. That one is free radical substitution. So let me just go over that once more very quickly. Okay, this was free radical. So now this was free alkanes. So this was free radical substitution, that in the presence of Cl2 and ultraviolet light, the hydrogens in the alkane chain or any alkyl chain, this could happen to any alkyl chain, any of the Cls would randomly get substituted. So that was the reaction. And the mechanism of the reaction was, I mean, this was the overall reaction, that HCl was produced as a byproduct, and you had any one of the hydrogens would get substituted by Cl, and they could all be substituted by Cl. The mechanism of the reaction was this, that the mechanism had 3 steps. Step number 1 was initiation, which was that in this step, free radicals were formed. Free radicals were substances that had unpaired electrons. So due to UV light, ultraviolet light, the Cl2 bond would break homolytically. It would break homolytically, and it will split into 2 atoms, 2 Cl atoms. The term free radical, we wrote down the definition of free radical. The term free radical was this thing. Yesterday we did free radicals as well. So free radical meant it's represented by a dot. It's a species that has unpaired electrons. It's very reactive, and what unpaired electrons means that its bonds are not complete. So any molecule or any atom whose bonds are not complete, like if you have a Cl atom, the Cl electronic configuration is this. So one of the orbital of Cl it's got unpaired electrons. So it will try to bond with something. If you have CH3 molecule, then the CH3 molecule, the carbon bonds are not complete, so it's going to try and bond with something. If you have an OH, the oxygen 8 electrons are not complete, so it will also try to bond with something. So anything that has incomplete bonds, that's a free radical. So in this case, in free radical substitution, you had 3 steps. Step number 1 was, spinner, you had UV light falling onto it, and the molecule would split homolytically, which means breaks the Cl2 bond homolytically. What that means is that the electrons, they get divided equally, which basically means 2 Cl atoms are produced, and those Cl atoms are free radicals because their bonds, Cl will try to bond with something because it needs 1 electron. Propagation is the next step. Once those Cl radicals are produced, the Cl radicals are looking for electrons. The Cl wants 1 electron from somewhere. So what it will do is that it is going to attack the Cl radical or Cl atom, is going to attack one of the hydrogens in the carbon chain. It could be any one of the hydrogens. And it will steal that electron from, the H is right now bonding with the carbon on the left side. So instead of sharing electrons with carbon, the electronegative Cl will pull that electron and it will bond with it. So the H, instead of bonding with the carbon over here, it will start bonding with the Cl over here. So carbon is now short of a bond, and carbon becomes a radical because carbon is supposed to make 4 bonds. At the moment, it's making 3 bonds. So it will try to find someone to bond with. So it's a very reactive ethyl radical. The next step of propagation is that the ethyl radical would attack a Cl2 molecule because the carbon wants to bond with something. It needs to share its 4 electrons. Its octet is not complete. So it's going to steal Cl's electrons. Cl, instead of bonding with the other Cl, would then start bonding with this carbon over here. And the Cl radical would be formed again. And the propagation step would continue. So the Cl radical is formed again. Cl radical will then again attack one of the hydrogens. It's going to steal one of the hydrogens. So let's say it steals one of the hydrogen over here. It would form HCl. The carbon is again short of 1 bond, and it becomes a radical. That carbon would then attack a Cl2 molecule. It will grab one of the Cls and bond with it. the Cl is now short of one bond. It's a free radical, and it just keeps on continuing. The Cl radical is reformed. The Cl radical goes, attacks one of the hydrogens, steals that hydrogen, bonds with it, HCl. The carbon is now short of a bond. It's a free radical. So the carbon free radical would then go and attack one of the Cls and bond with it. And a Cl radical would be again produced. And the steps continues to repeat. Cl radical then attacks one of the hydrogens, bonds with it. So the same two steps continue to repeat over and over again. Is that clear?
Yes.
Yes, sir.
Okay, so far, this is free radical substitution. UV light helps in producing the first radical. And then those radicals, they start stealing the hydrogens. They form HCl, radical formed. The radical grabs one of the Cl from the Cl2 molecule. The Cl radical is again formed. So the process just continues. It's like a chain reaction. And then you have, thirdly, you have a termination step, which is, the termination step is that what was the issue over here? Why was the reaction propagating? Because a Cl radical was short of a bond. So it would go and steal one of the hydrogen atoms. And if it does that, then that carbon is now short of one bond. So that carbon would then grab one of the Cls and bond with it. Then the Cl would again be short of a bond. Now, termination is that since so many free radicals are getting formed, why don't the free radicals just join with each other? Like in all the previous steps, remember there are thousands of molecules. So if you have this free radical, and let's say you have a Cl radical as well. So this reaction is happening thousands of times with thousands of molecules. So why don't these two sort of join up with each other? Different radicals would be produced at different stages. And there's going to be a mixture of radicals. So why don't this Cl wants one bond, this carbon wants one bond? Why don't they just join together and they form that bond? If they do that, then the free radicals will get used up. So any two random free radicals can simply join up. Similarly, over here, you've got this radical, you've got a Cl radical. Why doesn't this Cl radical just bond with this carbon atom and the reaction should stop? So instead of the reaction propagating endlessly, the reaction would terminate because now you've got a stable compound. A stable compound having complete bonds. Similarly, what can also happen is two radicals of the same type can also bond with each other. So, I mean, these radicals were produced in the previous steps. If you had noticed in the propagation step, somewhere over here, this one, you had this radical being produced. So maybe two of these radicals, why don't they just join up with each other instead of propagating the reaction? You had one radical and there would be another reaction going on. It would produce another radical. This carbon needs a bond, this carbon needs a bond. Why don't they just bond with each other? So they can simply bond with each other as well. So you clear as this is the termination step. Is this clear?
Yes.
Sir, do we have to draw the curly arrows in the steps?
You should preferably, like this. But the free radical mechanism, like the entire mechanism, has appeared very few times in the examination. Plus, there's a problem with the marking scheme as well. The marking scheme is like whoever makes the marking scheme, they're very terrible with drawings. So there are a lot of times they leave the curly arrows, but the question would be very specific. Like even if you get the question on mechanism, they are very specific that they ask for the curly arrows. So they will tell you. Preferably you should draw curly arrows. But I think if they hadn't mentioned it, then you can write the reaction without the curly arrows. And also remember one thing, that it's a half arrow, it's not a full arrow, because it's the movement of one electron. So this electron, this electron comes over here and they end up sharing electrons. This electron goes back. So it's a homolytic fission that's happening. So half an arrow should be drawn. Now coming back to the question. So remember one thing, that the termination products have an integer multiple of carbon atoms of the original molecule. Like if you start off with ethane, you're going to get chlorine substituted ethanes. Like it's going to be ethane with chlorines getting substituted, but you can also get a 4-carbon atom molecule. I mean, 2 ethyl radicals can sort of join up, and that would result in a 4-carbon atom molecule. So if your original molecule is 2-carbon atom, the product could be 4 carbon atoms. If the original molecule is 3 carbon atoms, the product could have 6 carbon atoms. Is that clear?
Yes, sir.
Yes.
Yeah.
Okay, so coming back to the question, the first, he's saying, what is the first stage? The Cl-Cl bond is split homolytically. That was the first stage, right? 1 electron goes back to this 1 electron, and that results in the formation of 2 Cl atoms, which are radicals because they are short of bonds. As anyways, let's ignore CFCs for the moment. Here's another one. When octane is subjected to catalytic cracking, which compounds can be obtained? So let's go through cracking very quickly if we hadn't done so far. So I'll just I'll quickly talk about cracking. Can anyone quickly tell me what is the purpose of cracking?
To convert less valuable light chain alkanes to smaller, more valuable alkanes.
Okay, so when you have crude oil, there are all sorts of compounds that are produced. So, and cracking is specifically for hydrocarbons. It's the hydrocarbons that are, I mean, you're very specific about cracking. It's the hydrocarbons that you obtain from crude oil. Now, remember one thing, that crude oil, they don't really have other functional groups. Like it's very rare for crude oils to have an OH group or to have a carboxylic acid group or have an aldehyde group. Crude oil, the stuff that you get from the Earth's crust, that is mostly alkanes and alkenes. That is what you get, because after billions of years, the organic compounds that you get naturally, like ascorbic acid or malic acid or vinegar, they have lots of natural, we are an organic compound, so we've got amino acids and stuff. So you've got lots of groups attached. Crude oil doesn't really. It's just a bunch of hydrocarbons. It's a mixture of hydrocarbons. So long chains are not very useful. Can anyone tell me why they're not useful? Long chain hydrocarbons are not useful.
They can break easily.
No, they don't.
They can break easily.
No, but the thing is, what do you use crude oil for? Mainly for producing energy, right? That is the number one purpose of crude oil. So long chain hydrocarbons have certain properties, that bigger molecules have van der Waals forces, more van der Waals forces. So whenever you have bigger molecules, you're going to have more van der Waals forces. And if you have more van der Waals forces, that means you're going to have higher melting and boiling points. So you're going to have higher melting points and boiling points, plus it's going to be more viscous. And they would be less soluble as well. So they would be very thick because the force of attraction is more. And the most important thing is they're also going to be less flammable. They will not mix with oxygen. Like candle wax does not really mix with oxygen very well. So they would be less flammable as well. So bigger molecules are not useful. And these are some of the reasons, because the van der Waals forces are so strong. And because of the stronger attraction between molecules, they are very viscous. They don't flow easily. And They have very high melting boiling points, so they are semi-solids, and they don't burn easily because they don't mix with water that well. Okay, is that clear?
Yes,
Yes,
sir.
So now these are broken down. Does anyone know what the conditions are for breaking a hydrocarbon into smaller, more useful chains? What are the
high pressure.
But you have to be very specific. Smaller, more useful. Useful chains. So it's basically this one. So it's basically a mixture of more useful chains. It's basically a mixture of alkenes, and hydrogen gas. And so anyways, you have to be very specific. Catalytic cracking is that you add a catalyst, which is SiO2, a mixture of SiO2 and Al2O3. And it's known as the rock that contains this, that's known as pumice. SiO2 is basically sand. And the Earth's crust, remember the three main minerals in the Earth's crust. One of them is silica. So one of them is silica because SiO2 is sand. Most of the rock that you see around you, that's basically SiO2. The second most abundant thing, like if you take dust, like if you take a bucket full of dust, it's going to have Al2O3, and the third most common mineral in the Earth's crust is magnesium oxide. So whenever you see dust or whenever you see clay, it's got sand, it's got Al2O3, plus it's got magnesium oxide. So pumice is a type of pumice or zeolites. So pumice is basically a type of clay, which a lot of people keep in their homes as well. So let me just show you what pumice is. Maybe if I can. Just very quickly, this is what pumice looks like. It's a type of rock which has a very high surface area. A lot of people use it for removing the excess skin on their feet. Like a lot of people have this in their homes. So anyways, the purpose of pumice is that it increases the surface area so that the sand and so the reaction could happen at a faster rate. But those are the conditions that the temperature is kept above 450 degrees centigrade. So those are the conditions, and that is known as catalytic cracking. There's another type of cracking, and that's thermal cracking. Thermal cracking is you just take the temperature to very high. Thermal cracking is requires much tougher conditions because you're not using a catalyst. Temperature should be greater than 700 degrees centigrade, and the pressure is upwards of 70 atmosphere. So that is thermal cracking. So if you're being asked, just write catalytic cracking because that's the one that's frequently used. So anyways, bigger chains, they get broken down into smaller, more useful chains. What's so useful about smaller chains? They are more flammable. They have lower melting and boiling points, which is a good thing because they would probably be in gaseous state. And they would be more flammable. Because if they vaporize like petrol octane, it vaporizes very quickly. So it mixes with oxygen very quickly. So it's going to be more flammable. Why? Because they have less van der Waals forces. So that's all about cracking. And the other thing that they might ask you about is equations for cracking. So equations for cracking are simple. That remember, it's going to be a mixture of alkenes, and H2. So if I write an equation for a big molecule that's breaking down, all you have to do is, like if I want to crack this, now there's no one equation because it's a random process. So if I crack this, I'm going to get a bunch of smaller molecules, and the smaller molecules must add up to this big molecule. So maybe I got an alkane. An alkane has a formula of, let's say I have a 10 carbon atom alkane. So make sure you get the formulas right at CnH2n plus 2. And maybe I get an alkene, a 40 carbon atom alkene. So I get C40 and H80. So that is Cn H2n. Now what is left is 40, but there's another 10 carbon atom, and I think that would be an alkene as well, C10H H20. So what I've done is I've made one of them is an alkane. The other two are alkenes by looking at the formula. But the thing is that all of them, they should add up to be equal to, they should add up to be equal to the original molecule, which is C60H H122. Is that clear? Is this adding up? You clear?
Yes.
Yes.
Okay, so you'll be given one molecule, and remember about alkenes. Adding double bonds would remove 2 H's.
Sir, a question.
Yes.
Let's say they ask us to like split up a product into certain like smaller products, so we can choose any ones, right?
Yeah, it's a random process. It could be any equation.
Oh, okay.
Okay.
Thank you.
So sometimes they'll give you this, and they'll ask you what's the third molecule. TK, do you get my point? So it's a random process. You can get anything, and it's and also remember that whenever an alkene is formed, the formula is CnH2n. It doesn't always work. It only works if it has one double bond. If it's got 2 double bonds, then you remove 2 H's, 2 further H's. Like let's say I have another molecule, and this time it cracks in a different way. Like each one is going to crack in a different way. So if there's a second molecule, then that molecule would be cracking in a different way. So let's change that. Let's make this C25H50. So what should be the other one? That should be how many 25 plus 10, that's 35. So 35 and 60. I think I'm still short of 25, right? Does this work? Is this fine?
Yes, sir.
Yes.
Okay.
Yes.
So now so it could split in any way possible, as long as this is an alkane, this is an alkene. Now sometimes the alkene can have more than one double bond. So if it's got another double bond, to remove 2 more H's. Maybe let's have 48 hydrogens, right? This is what I mean. Like let's say I have an alkane. The point I'm trying to make is don't rely completely on the general formulas. So if I have an alkane, if I add 1 hydrogen, I would have to remove 2 hydrogens from the molecule, which is why instead of being CnH2n plus 2, it becomes CnH2n. If I add another double bond, I would have to remove 2 more hydrogens from the formula. Is that clear?
Yes.
So the molecule is going to have, the molecules that are going to form are going to have alkenes and alkanes. But it's not a guarantee that it's going to have 1 double bond. It might have more than 1 double bond. If it has 1 double bond, it's CnH2n. If it's got another double bond, maybe there are 2 double bonds in the molecule, then it's going to be, they remove 2 more hydrogens from it. It's going to be C25H48. Now, is this all adding up to this thing?
No.
So there's a possibility of H2 gas as well. So if you're short of hydrogens, what you should do is you should add H2 gas molecule. right? Is that clear?
Yes.
Yes, sir.
Okay, so this one has more than one double bond. So be careful. The alkane general formula is always CnH2n plus 2 unless it's cyclic. Like either adding double bonds, adding serial bond C will remove two H's from the formula, or cyclic structures would also have two hydrogens less. Because if I make a cyclic structure and that's an alkane, like initially, let's say it's not cyclic. So this one at the moment is not cyclic, so it has how many? It has 8 hydrogens, right? It's got how many? It's got 10 hydrogens. But if I were to make it cyclic, then I would have to get rid of the 2 hydrogens over here, and I would have to join the 2 carbon atoms together. Do you get my point? That if you want to make a structure cyclic, the formula loses 2 hydrogens. Is that clear?
Yes.
So always remember these are just small points. Make sure you write them separately. Adding a double bond every time would get rid of 2 hydrogens. Making the structure cyclic would also get rid of 2 hydrogens. So anyways, coming back to the question, this is all about cracking. These are the conditions. So coming back to the question, what was the question? He said that octane is subjected to catalytic cracking. So what's the formula of octane? I mean, it's an alkane. So what is the formula? How many carbons does it have?
C8.
8.
And H18, right?
Yes.
So he's saying that it's subjected to catalytic cracking, which is Al2O3 SiO2, which is pumice, temperature greater than 450. Can you get any of these when you crack this? What products can be formed? I mean,
Honestly, you can get
all of them?
You
Yeah,
can
you
get
can-
all 3.
So basically,
Yes.
what you're going to get smaller. You're going to get. I mean, what's the rule? You're going to get smaller alkanes and alkenes and H2, right? So you're going to get all of them. This is 2 carbon atoms. You're going to get a 4 carbon atom alkene. You can also get, I think, how many carbons is this? This is 6 carbon atoms, right? So you're going to get a smaller thing. That's it. Is that clear?
Yes.
Yes.
So now the next question is, you've got which pollutant is formed in the internal combustion engine is removed by the catalytic may become. Which one would form acid rain?
Nitrogen oxide.
Okay, that's it. I said, anyways, this one. Alkanes produce carbon dioxide and water as an important exothermic reaction. Which line in the graph shows the relationship between the carbon atoms and the number of moles of oxygen needed for complete combustion? Now it's going to be a linear increase. Like if I have the first, this is the number of carbon atoms, like, so I'm going to start with 1 carbon atom. You burn a methane molecule, right? So it produces CO2 and H2O. And if you balance this would be 2H2O and this should be 2O2, right? The next carbon atoms, if I increase the number of carbon atoms, because remember, one axis is the moles of oxygen and the other axis is the number of carbon atoms. So if I take C2H6, which is ethane, and if I react it with O2, it's going to produce CO2 and H2O. Now, in this case, there's going to be 3 H2Os and there's going to be 2 CO2. So that's a total of 7 oxygens. So I'm going to get 3.5 O2s over here. The next one is propane, which is C3H8. If I do the reaction and I burn it, it's going to produce CO2 and H2O. There's going to be 3 CO2s and 4 H2Os, and that's 6 plus 4, 10. So that's 5 O2s, right? Now there's a linear increase in the number of oxygens. It's 2 to 3.5. What's the increase? That's 1.5, right? 3.5 to 5 is 1.5 again. What should come after this one? It should be 6.5. I mean, you can try this. It's if I have butane, which is C4H10, and I make a balanced equation, it's going to be CO2 and H2O. There's going to be 4 CO2s and there's going to be 5 H2Os. And if you balance this, that's 4 2s are 8, 8 plus 5, 13. 13 is 6.5 O2. So it's a linear increase. Is that clear?
Yes.
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 And this applies to all hydrocarbons as long as it's the same functional group. I mean, I can add this point over here that when you burn something, combustion, what happens is every time in the homologous series, the difference between neighboring or adjacent families of compounds is. So let's just quickly talk about combustion a bit. First thing, complete combustion with excess oxygen is going to produce like if I have any hydrocarbon CXHY, it's going to produce what it's going to produce carbon dioxides and H2O, but only if it's in excess. And if it's not in excess, if it's incomplete combustion, so if I burn it in a limited supply, what will I get? I mean, what are the products in a limited supply?
CO.
Carbon monoxide and water.
Not only carbon monoxide, you're also going to get carbon, which is soot, and plus H2O. So this is the black substance that you see, that soot, and carbon monoxide is the poisonous gas, which causes choking. So it causes choking. So you've got 2 types of combustions, and always remember that in any homologous series, and this is talking about within a homologous series, like within alkanes, within alkenes, as number of carbon atoms increases, as number of carbon atoms increases by 1, so it increases by 1, then the oxygen molecules needed would increase by 1.5. I'm writing this down because it's a waste of time to measure this while doing a 1-mark MCQ. So you must remember this information. And the reason this happens is, like, if you take any let's take methanol, for example. And if I react it with oxygen, right? It's going to produce CO2 and H2O. And if you balance this, it's 1, and it's going to be 2 H2Os. So that's a total of 2 plus 2, 4 oxygens. So there's 1 already there. So this would be 1.5 O2, right? So you're going to have 1.5 O2. Now the next one, if I take the next homologous series, it's C2H5OH. So if I take the next homologous series, C2H5OH, this should be CO2. I mean, you should have, without making the equation, you should know that the next in line, if it's methanol, ethanol will have 1.5 more oxygens needed for combustion. So it's going to be CO2 and H2O. So I think there's going to be 3 H2Os and 2 CO2s, and that's a total of 7 oxygens on the right side. There's 1 already there, so you need 6. So this would be 3. Is that clear that the difference would be 1.5? If you're talking about the next one, it's going to be it's going to take 4.5. Is that clear?
Yes.
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 And the reason is that every time you move to the next homologous Cs, the difference between the two molecules is of 1 C and 2 H's. So they have a difference of CH2. So that means one extra carbon dioxide would be produced and one extra H2O molecule would be produced. So make sure you kind of keep this pattern in your mind. As anyways, coming back to the question, this one was relatively easy, you just had to. Now this is addition reaction. Where would the bromine get added? Kahan pe add hogi?
Alongside the double bonds.
So it's
So B.
So it's going to be B. So the bromine will get added, and it's Br2 in tetrachloromethane, which is an inert. Tetrachloromethane is CCl4. So tetrachloro means methane with 4 chlorine. So there is no H. So it's an inert solvent. So Brs will get added at these positions. There's actually another bromination reaction, which is slightly. If we have this over here, just a second. So there's this other with bromination. So we didn't write this over here, but I'll just quickly tell you that there's another bromination reaction. What happens in that is that if aqueous Br2 is used, remember bromination conditions, there were two. You can either choose to use aqueous or you can use inert solvent. Now, inert solvent is inert. It will only give you Br, but if the solution is aqueous, what will happen is that alongside this molecule, there's a small chance, not a big chance. There's a small chance that instead of 2 Brs getting added, you might get, so instead of 2 Brs, you might get 1 Br, and the other one would be OH. So that's a small chance, and the position of the OH could possibly be different as well. So it could be the other way around as well. That your OH could be on the left side and the Br could be on the right side. So make sure that when you have aqueous solutions or aqueous solvent, the bromination, there's a very small chance of an OH group also getting inside that. So if they had given you an aqueous solvent, then the most likely product would be this one. But there would have been a small probability of 1 OH getting into the double bond as well. Is that clear?
Yes.
Yes.
Yes, sir.
So let's try and do these questions in the next class then. Okay. Okay.
Okay.
Take care. Allah Hafiz.
Okay. Thank you.
Okay, sir. Allah.